Hi everyone, welcome to this continued series on understanding sense of data and pre-processing steps. In this particular video, we will talk about scaling as one of the pre-processing steps. In the previous video, we talked about encoding, and then previous to that, we had outlier detection and cardinality assessment as our topic. In this particular one, I'll be touching upon scaling and normalization techniques. We'll discuss why we need scaling and what are those methods for scaling. Scaling in data science refers to the process of adjusting the values or range of values or magnitude of numerical features in a data set. The goal of scaling is to bring different features or different columns with varying range of values to a common scale or similar scale. This step is quite crucial in some of the machine learning models that we choose, but there are machine learning models which are not impacted by scaling. We will discuss which models are impacted, not impacted when we come to the machine learning topic. But nevertheless, in this video, we'll talk about the methods for scaling data or normalization of the data. Let's get started. So what is scaling? It involves transformation of values in a column or variable to a specific range. Now, this can be one of the methods. The other method can be standardizing the range of values. So these are two methods which are typically used when we talk about scaling or normalization. The methods popular are called min-max scaling and standardization and robust scaling. Standardization is essentially the z-score transformation that we discussed in the basic statistics course. So let's look at each of these in terms of concept and pros and cons, and then subsequently I will be showing you the Python code implementations. So let's take an example here. Most machine learning models are actually impacted, or not most, almost all machine learning models, unless we are talking about some heuristics based or logical based machine learning. But most of the machine learning models that we talk about in AI, they only factor in the magnitude of the value in the column, and it doesn't know anything about the units. For example, let's say centimeter, meter, or kilometer. It doesn't matter whether you say 1 kilometer or you say 1,000 as meter. So it's going to look at that magnitude only. So one feature expressed in a very high magnitude may affect the performance of the model or decision of the model or prediction of the model. So let's take an example here. Let's say there are two lengths. L1 is 250 centimeter, L2 is 2.5 meters. Now, for us humans, these two are identical. They are same. L1 is equal to L2. But machine learning models, they have no ability to differentiate the two numbers. So it's going to heavily reward or heavily weight or more weight is given to L1 because it is expressed in a larger number, which in turn can cause problem to to the to in terms of the model prediction. So do we always need to scale? As I mentioned earlier, there are certain types of machine learning models, let's say naive Bayes or decision trees or random forests or boosting. So most of the tree based algorithms, they are not impacted or they don't need the data to be scaled. Nevertheless, it's a good idea to scale the data for the models which are based on distances or similarities. For example, nearest neighbor, neural nets, support vector machines, and so on and so forth. Scaling adds one step into the machine learning pipeline. So that means it is slightly, um, it's going to make the pipeline heavier by one additional step. But if you choose the machine learning models, let's say distance based or something to do with vectors, then scaling is a mandatory step. So let's talk about the min-max scaling. It's also known as min-max normalization. It's a technique which converts the data series between specific range. So you can mention the range. Let's say the range is between 5 and 10, or 0 and 1 is the default. So this is a formula which is used, and let me just give you the meaning of this. Let's say we have a column, the values are 1, 2, 3, 4, 5. So what we do, we find out the maximum. So the maximum is 5, the minimum is 1, and let's say I want to transform this one. So take the value, which is x, which is 3, minus the minimum. So this is the minimum 1. So that's going to be 2 over 4. So this value will be zero point 0.5. So what we're saying is when we normalize, the 3 will be normalized to zero point 0.5. And similarly, you're going to do for the rest of the values as in the column. So let's take an example here. Let's say we have a data set for a variable, and these are the values. And the first step is to find the minimum, and this is a formula that we will use. Then we find out the maximum, and then we use the scalar function, which is going to scale a particular value. For example, x is equal to 5, put 5 minus 2, which is the minimum, divided by the range of data, which is max minus minimum, which is 3 over 8. So the scaled value would be between 0 and 1 here in this particular case. But in Python, you can mention the range that you want. It could be 100 and 200. It can be 5 and 15. It can be 15 and 25, depending on what you actually want. But default is 0 and 1. Now you see the original data is converted to equivalent normalized value. So what are the advantages of min-max scaling? It preserves the relationship. Its proportional relationship among the original value is retained in the transformed value. It's quite simple to implement. Applicability to algorithms. It is very useful for models which are impacted by distance, magnitude, and the scale of the values. For example, support vector machines, nearest neighbor based algorithms, and definitely neural networks. There are some downsides of min-max scaling as well. It is sensitive to outlier. Why it is sensitive to outlier? Because the denominator is max minus minimum. Now, if these guys are having extreme values, then the denominator would be impacted. So normalization to a fixed range. So essentially, you will pass the range. By default, is going to be 0 and 1, but you can choose a particular range. So that requires some experimentation as well. And it's not robust to extreme values. That means if you have extreme values in the data column, then this method may not be appropriate. So what are the best practices for min-max scaling? Must handle the outlier. So make sure the outliers are treated, removed, or adjusted, moderated before you go for min-max scaling. Evaluate whether the normalization to a fixed range is suitable or not. Now, this requires some time. For example, the range can be 5 and 7, or 7 and 17, or 100 and 200. All of that needs to be evaluated before you choose the specific range for the scalar. Second type of scalar is essentially a z-scores transformation, which is nothing but standard deviation. So we talked about this in our Essential Statistics Primer videos. It essentially converts the value in terms of a z-score. So again, I'll show you what it actually means with given. Let's say we have a column and there are values here 1, 2, 3, 4, 5, and the mean is, for example, 2, standard deviation is zero point 0.5. Let's say I want to convert this 3. So what we do here, 3 minus the mean, which is 2, divided by standard deviation, which is zero point 0.5. So it is going to be 1 divided by zero point 0.5. So this is going to be 2. So that means I'm going to convert 3 to a transform value called 2. Now this 2 is in terms of standard deviation. That means 3 in my series is away from the mean by 2 standard deviation. That's what it means. So z-score transformation is all about transforming the values in terms of units of standard deviation. And this works quite well for data which is Gaussian in nature or normally distributed, sort of normally distributed, little bit of normal distribution pattern should be there. If not, then choose min-max scalar. So let's look at an example here again. Let's say the data series 258 and so on and so forth. So you're going to compute the mean. So let's say 5.8 is the mean, and then standard deviation, exactly this the method that we saw in our basic statistics class. So this is our standard deviation, and apply those mean and standard deviation to each of these value, and you get the transform. For example, the value 5 would be 5 minus the mean, which is 5.8, divided by standard deviation, which is 2.9. That's going to give you the transformed value. And you're going to apply to the entire set here, and the transformed array will look like these. Now, these values are units of standard deviation. So the advantage of standard scalar is it preserves the mean and standard deviation of the original data, making sure that it's suitable for Gaussian distribution. Outlier insensitivity. Standardization is slightly less sensitive to the outlier. It is sensitive to outlier, but it is slightly less sensitive because we are taking an average, and then average of the mean in terms of mean and standard deviation is slightly less sensitive to outlier compared to min-max scalar, but it is affected by outlier. So it's widely used in machine learning models if the data has a bit of normal distribution. So for example, linear regression, k-means, anything to do with distance or vectors, something to do with origin, neural nets, for example. Those are the models where we use standard scalar. So there are disadvantages as well. Standardization assumes the data is normally distributed. That means if the data is heavily skewed, then this method is not suitable. So if not, then you choose some other method. Let's talk about one more method, which is kind of best of the two. And in this particular case, we are going to scale the value or numerical variable in a way that it is not impacted by extreme values or outliers. This is useful when the data contains some extreme values or you're not sure if the data really contains extreme values. So in that case, robust scalar would be used. Now, the difference is in robust scalar is similar to min-max scalar, but here notice what we are doing in the numerator. In the numerator side, we are taking the median, not the mean, and the denominator is divided by the IQR, not the max minus the minimum. So that's not what we're doing. We're taking the central part, and that's how it is not impacted by or least sensitive to extreme values. So the formula is quite easy, similar to min-max scalar. The difference is here. Let me highlight where the differences are. So here are the differences. Instead, in the min-max scalar, we talked about it here in min-max scalar. This is actually the minimum value that we take. But here now we are taking the median. And this denominator in this case is equal to the range, which is max minus the minimum, which is not what we are doing. We are taking the IQR, and that makes this particular scalar less sensitive to outliers. So let's take an example. For example, here, this is a series here of values. We compute the median, first, and then we find out the IQR, which is basically 5. And then for each of the value, substitute in the numerator, the median, denominator, divide by the IQR, and that's the transformed value that you get, or scaled value for the original value. So the 5 is now minus 0.2. Now you can apply this to all the values in your data or data column, and that's the resulting robust scaled values. Robust scalar is pretty much the choice in most of the data science project. I'm going to show you the Python demo, highlighting or showing usage of each of the scalar that we discussed. Let's take a look at the scaling implementation in Python. You have scikit-learn package, preprocessing, and it has min-max scalar, standard scalar, and there is one more which is robust scalar here. So these three are popular scaling methods or libraries here. There's a column transformer also, which is a framework essentially, not a scalar, where if you decide to use mix of min-max scalar and standard scalar. Let's say for one column you want to apply min-max scalar, and few other column you want to do this, and for rest of the column you want to apply robust scalar. Then you have to mix or combine all of these methods into a columns. Anyway, so let's take a look at each one of them: min-max scalar, standard scalar, and robust scalar. Here is the min-max scalar with the numerator, the value, the minimum divided by the range of the column. So let's take an arbitrary data set. The column is 10, 20, 30, 40, 100, 200, 300, and so on, so forth. So you need to call the min-max scalar, provide the range. You can provide the range, let's say 10 or 15, or you can choose 0 and 1, which is anyway default. So if you don't even mention this, it is going to be 0 and 1 anyway. So first is instantiation of the object, and then that's the scalar for you. The range is 0 and 1. And then after that, we fit the data. That means we provide this data. Now, when you provide this data, the scalar will find out the minimum and a maximum for each of the column. Okay, so, and you can take a look at it, the object where the data minimum contains the minimum for each of the column and the maximum for each of the column, and so on and so forth. And these are the values here. Then you can transform the original data by applying the transform method. Now you notice the data which was originally like this now is transformed to scaled representation. Let's apply this to a data set, and this one is available on my GitHub. So when you run, there should not be any problem. And here is the PIMA dataset, which is related to diabetic patient. And you notice here the columns are having multiple or variations in the value. Is 1 digit, 3 digit, 2 digit, fractions, and so on and so forth. So these are ideal candidates for scaling. So read your data using pandas, and after that extract only. So we don't want to scale the outcome column here. The last column is outcome column. We don't want to do that. So just extract the first 8 column, which is about the predictor column, and the last column is outcome, which we don't need to scale. So these are the columns here. So save the data before scaling, just to compare how the distributions look like when you scale after applying min-max scaler. So before scaling, anyway, this is the original data. Now we are going to call min-max scaler. Fit and transform together. You can do both of these together to convert the original data into the scaled. So now after scaling, you're going to see all these fractions of for each of the value in the original data frame. So let's bring the scaled data into a data frame so we can do some plotting. So let's see, we are going to plot the column before we scaled and after we scaled. Let's compare the two. That's how the data was. For some column, the values were very high, and for other column, the values were very low. Now, after scaling somewhat, a better representation has emerged. You can see here there is quite comparable scale for all the columns here. I hope this gives you a fair understanding of the benefit of scaling. Now we will do the same thing with standard scalar. The formula is the same. If you remember this, just for recap, the numerator is now having x minus the mean divided by the standard deviation. The idea of standard scalar is to transform the values in terms of standard deviation. So the same data set, PIMA, read it, put it in a data frame, take only the predictor column, not the outcome column, and then save it into a data frame, apply standard scalar, fit the data, and then after fitting you can evaluate and see what is the mean for each of the column and the standard deviation for each of the column. Then transform your data, and after transformation you can bring it to or save it into a data frame. So we can do a similar comparison here. So these are the plots for each of the column, and now you see here is much better representation than the min-max scalar. The transformation is quite better. If you see here the min-max scalar, it is okay, not a bad transformation, but standard scalar does much better here. And why it does better is the original data is Gaussian in nature in this particular data set. So you have to evaluate which scalar is better by trying out the different the scaling techniques. Now, robust scalar is again a method where we are not sure if the data contains any extreme values or not. So just go ahead and use robust scalar. It's going to give you a better result or than min-max or standard scalar if you had outliers or extreme values. So read the data again, and save it into a data frame before scaling. Then robust scaler, call the robust scaler, fit and transform, and this is your scaled representation of the original values. Now you can compare before scaling and after scaling. You can see here is similar result like standard scalar. So it means that this the data set does not have the problem of outliers in any of these columns. Nevertheless, you should actually evaluate each of these models, each of these scaling models, and see which one is appealing or which one is more effective for your data set. So that was the demo on the scaling techniques. I hope you liked the presentation. We'll see you in the next video, and then the next one is going to be on transformation, attribute transformations, and some other topics like data imbalances and so on and so forth. Have a great day, guys. We'll see you in the next video.